we now move to the discussion session about the asynchronous talks. Can we see the list of the talks? Okay, very good. Thank you very much. So also here you can write in the Q&A session your questions. Please always specify to which speaker you intend to ask the question. I would like now to ask all the speakers who uploaded their recorded videos with the talks, which you might had a chance to look at, to introduce themselves. In the meantime, people can start to write the questions they have, and then we will go to discuss the questions which can be posted in the meantime. So please, Aphrodite, start, and also, if you agree, enable everybody the camera, if it's okay for you.
Perfect. Okay, I hope that you can hear me. Hello, everybody. My name is Aphrodite. I'm a 50-year graduate student at MIT, and I have been working on the extraction of cross-section results using data from the microbone detector.
Okay, thank you.
Hello, my name is Julia Gerlein, and I spoke about CPU violating neutrino non-standard interactions in long baseline accelerated data to resolve the slight tension between the T2K NOVA data we just heard about.
Thank
Hello,
you.
everyone. Yeah, my name is Marco Grassi, and my talk was about the June experiment. It is a reactor neutrino experiment taking place in the south of China.
Thank you.
Hi, I'm Andrea Zani. I'm giving the talk about Dune in place of Melissa Uchida, who is the chair of our speakers committee. I'm a postdoc from INF Milano. Nice to meet you all.
Thank you.
Yeah, hi, I'm Tobias. I'm a PhD student based at UNSW in Sydney, Australia, and my talk is on the singly charged scalar singlet as the origin of neutrino masses.
Thank you.
Hello, I'm Véronique Van-Eloek. I'm associate professor at Université de Paris and APC laboratory. And I was talking about the Chem3net Orca water Cherenkov detector being deployed in the Mediterranean Sea.
Thank you very much. Veronique, beautiful picture behind you. Okay, so let's start. Thank you for the introduction, and now let's start to go in the order of as you introduced yourself to the questions. If the time is left, we can then do random questions. So, Aphrodite, can I ask you maybe a stupid question from somebody from out of the field? By inclusive cross sections, you mean that you require just the muon in the final state, or is there something more in depth in that term?
So by inclusive cross-sections, we mean that we have a neutrino of a given flavor incoming. That would be either an electron neutrino or a muon neutrino. And then in the final state, we have the corresponding lepton, which means an electron or a muon, depending on the incoming probe. But then also in the final state, we allow anything else. That means that we might have protons, we might have pions. We allow all those possibilities. We are not looking at more exclusive states, which means we don't narrow down the number of pions or the number of protons.
I see. Okay, so this is, and by exclusive you mean that you search for a specific final state.
Topology, exactly.
Okay. Then I would have another question, if I can. So you have shown in your slides that there is the particular data and Monte Carlo disagreement for the forward scattering muons. Is there, I mean, any idea why it is? It's instrumental. There are more backgrounds, worse resolution, or I mean, it's probably not physics, right?
Actually, we believe that it is related to the backgrounds. The reason why I'm saying that is because if you remember, I don't know if we can take a look at the slides and the corresponding consistent picture slide. So what the reason why we gathered all those results on the same panel is because as we move to from more inclusive results to more exclusive ones, what we observe is that this deficit, this data Monte Carlo disagreement intensifies. So this means if you go around, I think it has to be around slide 20 and maybe a little bit further down. Okay, perfect. This is the one, one slide behind. Slide 21. Perfect, that's the one. So what you can see in this picture is that as we move forward, as we move from the inclusive case here on the left, what we see is an excess of our Monte Carlo with respect to our data. But the moment that we start moving to more exclusive cases, which means that we allow any number of protons in the final state, or on the right-hand side, if we constrain the number of our protons to be identically one to make a quasi-elastic-like measurement, you see that the deficit becomes more pronounced. This means that most likely, this is the very forward region is the one what is dominated by our backgrounds, the backgrounds that we subtract from our data. We believe, and this is our best candidate right now, that this is not a reconstruction issue or exclusively a reconstruction issue. Most likely, this is because of the backgrounds, because of the underlying Monte Carlo that was used in our analysis.
I see.
So just to close this story, if you go closer to the end of my presentation, literally the second to last slide, the wealth of results, a little bit further back. Okay, perfect. So here in this case, you can see that we have a wealth of results that are going to follow. All those results are going to incorporate the improvements that I had the chance to talk about closer to the end of my presentation. While those analyses that are presented with multiple protons in the final state and with a single proton most likely are going to be repeated and are also going to be extended in terms of other kinematic variables. And hopefully we will manage to reconcile the deficit that we saw in the very forward direction.
Okay, thank you very much, Aphrodite.
Sure.
I would have a question to Julia. Maybe again, you have mentioned that there is a maximal allowed value for the Yarlskog invariant of 0.096. Could you comment from where does it come from?
Yeah, so this just comes from the expression of the Yarlskog invariant as a product of all the different mixing angles and delta. And if you just totally maximize all the allowed allowed values, you obtain this maximal value of the Yarlskog invariant. Yes.
Okay, so it's based on the measured values of the mixing angles there, right?
No, it's not. It's not based on the measured values. It's just the maximal values for the mixing angles you can put into this expression, independent of
okay, so it's really maximal. It's theoretically, it is not okay.
Exactly. Totally maximal, yes. And
okay,
then that is maximal value to what has been actually been measured, or what is the current bound on the Yarlskog invariant we have right now.
Okay, thank you very much. And I would have another question. So you have mentioned that the disagreement between T2K and NOVA results is about 2 sigma. And then you say that when you let the non-standard interaction to be introduced in your theory, then there is a preference for the normal ordering, right?
Exactly.
But what I somehow did not understood that what is the residual, is there any residual difference or tension even with the non-standard interaction allowed? For example, for the inverse ordering, there is some residual disagreement, which is bigger than for the normal ordering. That is how I understand it somehow.
No, so in the previous talk by Anna, we saw that in the inverted ordering itself, the NOVA and T2K data, they agree much better with each other. This disagreement, this was if you have in the normal ordering, there was this disagreement between the two preferred values of delta.
Okay. I've seen thank you. I have a question to Tobias from Pedro Pereira. What are the motivations, theoretical or experimental, behind introducing a singly charged scalar singlet?
Well, I think there are at least two good reasons for that. First of all, there are a few well-known models of radiative neutrino mass generation which feature this particle. For instance, the Z model or the Z-Babu model. And there are also experimental results which seem to indicate that there's a slight deviation from lepton flavor universality in charged lepton decays. And this singly charged scalar singlet is an attractive candidate to explain these anomalies or these deviations from universality, because it would contribute at tree level. Right? And we wanted to study both the experimental implications of this particle as well as its role in generating neutrino masses in a model-independent way. That was the motivation behind the project.
Okay, thank you very much. We have a question from Jeff Hyde asking again to Julia. On slide 17, you mentioned the limit of T2K of A T2K equals A of nova in your expression. Does this correspond to some physical situation? It seems like the value of A would be set by density and energy independent of NSC parameters.
Yeah. So exactly, thanks for bringing up my slides. So yeah, so what I did here was, okay, so what we did in our work, we also derived analytical estimates to obtain the expected value, the expected magnitude of the size of the NSI parameters needed to resolve the slight tension between T2K and nova. And this is what we see on this slide. So in the first line, you see the expression for the magnitude of the NSI parameter needed to resolve this tension, and we obtain values around 0.2. In 2 bullet points below, I basically just do a check if our analytical expression makes sense. So for example, in the second bullet point, the question was about if there is a disagreement between the value for delta preferred by T2K and nova, which is the case, but the matter potential in the matter effect in these two experiments is the same, then NSI cannot resolve this tension. So setting AT2K and AT nova equal is not it could happen, but this is not the case. And in this bullet point, I'm just showing that indeed we cannot resolve the tension with NSI if the matter potential were the same in these two experiments. So epsilon needs to go to infinity.
Okay, thank you very much. I would have a question to Marco Grassi concerning Juno. You have mentioned various potentials or physics potential of or goals of Juno. Could you please a little bit comment about the potential to measure geoneutrinos for Juno?
Yeah, sure. Maybe if we can bring up the slides, I guess in, let me see if someone can help me. This is on slide 6.
I did not see it in your slides, so maybe I missed it. That's why I was asking.
On slide 6, there is somehow an overview. Yeah, that's right. Or somehow the kind of capabilities that we have. So Juno is great in the sense it's so large that we'll be able to go beyond basically what is done by Borexino and by Cameron at the same time. So 400 events per year is really a stunning number. And the most prominent background here is just the IBD spectrums coming from reactor. Now, the good point is that we plan to we aim to understand the reactor spectrum very well, because that's the way we want to do our physics program, our main physics program in terms of oscillations. So somehow the capabilities that we plan to have in terms of geoneutrinos are really great. Now, the one thing that I need to mention is that the challenge we're facing now is really to understand eventually the source of the geoneutrinos we will get, meaning if they come from the crust or from the mantle. And so there is an ongoing effort within Juno to work together with geophysicists in China to somehow map the crust around Juno in order to better understand somehow the composition and to disentangle the different, let's say, sources, eventual sources of neutrinos. But somehow Juno would really be one of the lead experiments in terms of geoneutrinos as soon as it comes online.
Okay, thank you very much. If I could come back to the question of the to Tobias about the singlet. Could you please comment about what experimental observation could confirm your theory, or do you have any predictions like how the charge scalar could be discovered eventually?
So it depends a bit on what structure of neutrino mass generation one considers. So maybe if my slides could be brought up to illustrate that. Right. Could you maybe briefly go to should be slide further? So there here I distinguish between the two cases of neutrino mass generation, and because they have different phenomenological consequences. So for instance, if you can you go a bit further? So here one immediate consequence of these this mechanism here is that in the linear case, for example, all three neutrinos will be massive. So that means that also the lightest neutrino will have definitely a non-zero mass, and it could even be what is compatible. Like it could be as large as what is compatible with the current bound from Planck data, for example. Whereas in the quadratic case, which would be on slide 7 or so. So here, no, the previous one, sorry. So here, the lightest neutrino would be massless, which in principle, I think, would be visible at experiments like Katrin, for example, where they measure the absolute neutrino mass scale.
Okay. Thank you very much.
And there are lots of other signatures, like branching ratios are very sharply predicted in a quadratic case. So decay channels. You get correlations between the rates of radiative charged lepton decays. Yeah.
Okay. Thank you very much. Then I would have a question to Andrea. I cannot resist, since I work in the field of solar neutrinos, about the potential. You mentioned that it's under study right now about the potential to measure solar neutrinos. So if you could comment a little bit more on that, in particular, if you have an estimate what resolution you expect that this energies between 10 to 20 MeV, where is the endpoint of the boron 8 solar neutrinos?
These studies are still at a level of complexity that is a bit behind with respect to, for example, supernova neutrinos, because for the solar neutrinos, we are really at the limit of the dune sensitivity. Mm-hmm. So first of all, we are dealing with what could be radiogenic backgrounds inside the detectors, because for solar neutrinos, we might have some backgrounds from the radiogenic contaminants in the detector modules that come from the detector materials. So first of all, there is ongoing an evaluation of which is the radiogenic budget of the detectors. Mm-hmm. And in this case, going from far detector 1, which is an horizontal drift single phase liquid argon TPC, to the detector 2, which is a vertical drift single phase liquid argon TPC, is helping actually, because in the vertical drift there is far less material for in the present design. So this should help. but I cannot give you numbers for the moment for what concern the resolution. The numbers that can be found on the slide with supernova neutrinos concerning the resolution at low energy might be taken with some grain of salt as a starting reference, but this is a different mechanism. So again, you can take them as a starting reference for the resolution of the detector components at those energy ranges, that energy range.
Okay. So I'm curious
here.
how it will be finalized.
Yeah, we are curious as well because it's very interesting. But as I was saying, it's really a study in progress. So
thank you very much. Yeah.
You're welcome.
Then we have a question from Mateusz Hostert to Veronique. Does ORCA have any sensitivity to glacial events as measured by IceCube recently?
So thank you for the question. Actually, ORCA targets atmospheric neutrinos in the range from a few GeV to a few hundreds of GeV. So it's a much lower energy with respect to the glacial resonance, which is expected above the PV scale. So ORCA will not be sensitive to that kind of event, but ARCA will. ARCA is the other branch of the Chem3net detector. So it's a much larger detector whose size is similar to IceCube. So it will be about 1 kilometer cube of seawater. And we expect that ARCA will indeed have a sensitivity comparable to IceCube for glacial events. So maybe of the order of a few events over the full lifetime of the experiment, which is expected to be order of 10 years.
Okay, thank you very much. We have a question from Sasha Tomalak to Aphrodite. Very nice resolution of tracks on slide 11. Question 1. What determines the displacement of the track? Is it different for electrons and protons? How it depends on energy of the particles?
Perfect. Okay. So just to be clear, there is no displacement for electrons and protons. The displacement shows up for photons. The reason for that being that we are talking about neutral particles that propagate inside our detector, produce, and then we see the shower. So the typical, this typical displacement for photons is something of the order of 15 to 20 centimeters, which is exactly the picture that you can see here in the middle. But for electrons and for protons, there is no displacement.
Okay, thank you. There are some more questions, but I will jump to other speakers' questions. You can then continue on Slack, or I come back to it if we have time. Mm-hmm. Chris Hilgenberg asked to, Lucas Berens asked to Julia regarding this NSC, the psi, there is also this tension of the solar parameter, solar versus Kamland, where NSC can be invoked as a solution. Is there any relation to them, possibly via some flavor symmetries in the NSC?
Yeah, so this slight discrepancy in the solar parameters, this could possibly be resolved with NSI epsilon EE, so a diagonal NSI parameter, whereas in our work for T2K INNOVA, we only looked at the off-diagonal NSI parameters. We also didn't have any particular NSI model in our mind. I mean, of course, maybe you have a model where you have this value of diagonal NSI parameter needed to resolve the tension between T2K INNOVA, and which simultaneously also gives you value of epsilon EE, which could resolve the tension in the solar data.
Okay, thank you very much. Then we have a question from Peter Denton to Marco. Can you comment on the status of the power plant construction operation?
Sure, that's a tricky question. If you can go to my slide 7, please. In slide 7, you will see that what I'm reporting here is that we plan to have actually 10 cores. What happened is that the right power plant, so the Taishan one, the one on the right, was supposed to be actually double. Now, out of the 4 cores planned, only 2 were built. And so this is why the total power was reduced from 35.8 to 26.6. But the good news is that this number is fixed in the sense these power plants actually do exist. And if we can move to slide 14, what I try to demonstrate here is that even if we reduce somehow, even by taking into account this reduced power, eventually we end up with the same sensitivity, with these 3 sigmas. And the reason being that somehow we managed to compensate through the detector. So we had better PMTs in terms of detection efficiency. We had better liquid scintillator. Now we have a better constraint on the isolated flux. So once you take everything into account, somehow we managed to compensate for it, and we keep this 3 sigma unaltered. But thank you very much for the question. Actually, this is indeed, this was indeed an issue, but we managed to solve it.
Okay, thank you, Marco. So it seems we have time to go back to the question of Sasha Tomalak to Aphrodite, her slide 11. So the second question was, what are the energy threshold of electron and photon detection?
So the typical energy threshold for those electromagnetic showers would be of something between 50 to 100 MeV.
Okay, we have one more to go.
Good.
How the electron-photon discriminating power depends on the energy going from 1 MeV up to 4 JeV.
Okay, so again, we have the best discrimination power starting from the threshold that I just talked about, roughly 100 MeV. And again, because of the booster neutrino beam line, which basically peaks at around 1 GeV, this discrimination power is mostly reliable in this region between 100 MeV and roughly 1.2 GeV. So, and if you go very quickly to slide 12, you can see what I'm talking about by the discrimination power being the energy deposition per unit length. So this picture is something that we can reliably reproduce and separate electrons and photons in this region between more or less 100 up to 1 GeV. I don't think we can go up to 4 GeV.
Okay, thank you very much. And I would have a question for Veronique. You have shown the predicting sensitivity to the Z/A ratio for Earth's mantle and core. So my question would be, do you think it will be possible to measure this ratio separately for the inner and outer core? The question why I ask is why I think it's only in the outer core when the seismological measurements foresee a 10% admixture of some lighter element which is unknown, while in the inner core it's not expected to be a lighter element, I mean lighter than nickel and iron.
Yes, so maybe the slide was not completely clear, so let me check the number of the slide. So I think you are talking of slide 16. So actually, what we intend to measure is indeed the zero factor of the outer core. So we keep the inner core fixed, and we measure the outer core. Yes, indeed, because that's why we can have a handle on the elements. Okay,
very good. Thank you very much. Then we have a question from Mateusz Hostert, again to Veronique, so stay on. How does the energy resolution in kilometer cube net compare to ice cube? Do we expect an improvement in water over ice? I'm thinking of how this impacts monoenergetic neutrino sources from dark matter annihilations, for example.
Well, again, it depends a little bit whether you are talking about ARCA or ORCA, because the energy range is completely different. And so the kinematics of the events, especially at low energy, have a stronger impact on the energy and angular resolutions. What we do have in water is a better angular resolution, because the scattering length of the photons is much larger in seawater respect to ice. So in that sense, it helps for directional resolution, but for energy resolution, it's, I mean, ice is a better calorimeter. So probably ice cube can collect more light because of the scattering than we can. And speaking about resolutions, I think we have of the order of 20 to 30% energy resolution, depending on the energy.
Okay, thank you very much, Veronique. I think we have used our half an hour dedicating to the discussion session of this neutrino panel. If you have more questions, the discussion can continue on the Slack, so don't be shy, ask the speakers.